Okay, welcome everybody. This is the next to last Energy and Environment Forum of the semester. So thank you for being here in what is sort of crisis mode for the semester. I know April is the time when everything is due and everybody is busy. So I appreciate everybody being here for a very special Energy and Environment Forum with Dr. Gross's last research seminar, which he told us we could call it for promotional purposes. Well, nobody on there knows that. There's hundreds of people in here right now. And so I know there's lots more people online. I've seen the people that are showing up online. So for those of you who are online, you should see a link at the bottom of your screen that will, you go to that link and you can enter in your questions for Dr. Gross, and we will feed those to him at the end of the seminar. Likewise, for folks that are in the auditorium today, we have a mic set up in the center of the room that you can go to and ask questions at the end as well. So if this is your first time at the Energy and Environment Forum, thank you for coming. This is our opportunity on campus to talk across disciplines about energy and environmental issues. So there's loads of opportunities for us to talk within our disciplines about things. It is very enlightening when you start talking about things with other disciplines to see how they respond and react. And so this is one of the few instances that we get to do this on campus. And so we're very happy to have you here today. We have one more of these for the semester. So if you like what you hear today, we will have Becky Trout-Frixell on April 28th, who will be talking about encephalitis in children in East Tennessee. Okay, so this is a One Health type of seminar that will be going on the 28th. So please put that one on your calendar. And we are already ramping up the series of speakers for next year. So if you are not signed up on our Baker Center mailing list, I would suggest that you do that, and then you will get notifications for all these seminars without having to rely on seeing our fancy, slick-looking posters across campus. Also, if you do want a copy of the video of today's talk, Lou, we are recording it. I didn't clear that with you. You're good with that, right?
It's fine.
Okay. So we are recording this. If you want a video, email Elizabeth Woody at the Baker Center, and she can send you the video link if you would like to use this for your class or something else. Okay. With that, I'll hand it over to Paul Armsworth to introduce our speaker today.
So thank you, Charles, and thank you everyone for coming out today. Thank you those who are online for joining us as well. It is a tremendous privilege for me to get to introduce someone to you today who he's a great friend, he's been a great mentor for many, many years to me, and I suspect to many others in the room as well. Luke Gross is a Chancellor's Professor, an Alvin and Sally Beeman Distinguished Professor of Ecology and Evolutionary Biology and Mathematics here at the University of Tennessee. Lou was the director of the hugely successful NSF Synthesis Center on the campus, NIMBUS, the National Institute for Mathematical and Biological Synthesis, for many years. He is currently also the director of the very successful Institute for Environmental Modeling that is now in its 24th year of operations. He has written or edited 9 books and numerous papers on ecological modeling and the intersection of mathematics and biology. Now wait for this one. He has brought in over $50 million in external research funding to the campus as PI. $50 million. He has taken on leadership roles with major academic societies. He's been a key contributor to national initiatives to improve STEM education in the country. He has been the president of our faculty. This is his 2nd term as our president of the Faculty Senate.
I'm a fool.
Separate to his academic life, many of you know Lou is a very active community member in Knoxville and East Tennessee. Lou joined our faculty and community in 1979. He is retiring from his full-time role this summer, and he is going to leave a very large hole. In recognition of all that he contributes, Lou will be the mace bearer at next month's graduation, the highest honor the university conveys on a faculty member. The Energy and Environment Forum is absolutely thrilled to have Lou with us today for what will be his last research talk on the campus before retirement. Please join me in welcoming Lou Gross.
Thank you very much, Paul. I was hoping you would just keep going and then I wouldn't have to say anything. But I really appreciate, first of all, the invitation from the Baker Center to be here to do this. And I also need to thank Charles and Charlie and Becky and Paul, who have organized this series over a very long time. And it's been a great way to introduce people to many, many different topics. Because this is my last talk, I'm going to, the typical thing would be to reminisce and do all of that. And I'm going to do a little bit of that, but then I'm going to think moving forward. So the first thing I'd like you to do is to close your eyes and think of 2 people who have had big influences on you in order for you to get to your career stage that you're at. Think of 2 people, and then when I'm going to count to 3, when I get to 3, say their names. 1, 2, 3. Okay. Thank you very much for doing that. I have the privilege of actually putting up the pictures of 2 of the people who very much influenced me and enabled me to get here today. And hopefully at some point when you give one of these talks, you will be able to put up the picture of the 2 people that you just mentioned, or perhaps others. Simon Levin was my PhD dissertation director at Cornell at the time and is now at Princeton University and is still going strong at 80 years old with phenomenal numbers of students and has won all kinds of awards and is one of the founders of the connections that I'm going to talk about between the fields of economics, social science, biology, and computational and quantitative methods. My wonderful colleague Tom Hallam was the person who actually hired me here, started in the math department, and basically worked with several other people to build the program that allowed us to be very successful in mathematical biology. And one of the things that we collaborated on for 20 years was a series of courses and workshops at the International Center for Theoretical Physics, which brought in developing country scientists from over 80 different countries, well over 1,000 people over the space of that 20 years. These were researchers and mathematicians and scientists to inform them about applications of mathematics and quantitative methods, particularly to natural resource management, conservation biology, and to epidemiology. And you never know what the long-term impacts of what you do will be. So this is a picture of Gideon Ngwa and Miranda Tico Oblanca. And Gideon was one of the students. His picture's actually, he's up there in that picture from 1996. And he is from Cameroon. He's on the faculty at the University of Boué. And he trained Mimi, Miranda in the middle, and Miranda trained Callistus on your right. Callistus was one of our earliest postdocs at Nimbus, at the Institute. Callistus is now on the faculty at the University of Florida. And just last year, this book came out that Gideon and Mimi co-edited in honor of Tom and Simon and my work 20 years before on helping develop quantitative methods and so on around the world. And of course, it's about infectious disease. And many of the people who I think have been working on COVID modeling can trace their lineage to people who were educated at these courses from around the world. I need to mention as well two people who are my wonderful close colleagues here, Sergei Gavrilets, who's in the room, and Suzanne Lenhart, who really built with me this program in quantitative and mathematical biology over a very, very long time. And there's all kinds of ways that you can estimate success for programs, for academic programs, in terms of papers, in terms of honors and things like that. And Paul already mentioned one other one. I'm going to point this out because I think it's pretty amazing. If you add up all the grants that Suzanne and Sergey and I have been involved with here, you take all of the F&A, it's called the facilities and administrative costs, the indirect costs that come back to the university, not to pay for our salaries or anything like that. It's just extra money to cover the costs of the research at the university. Add that all up. It paid completely for our salaries and our fringe benefits over our entire time here. 110 years of effort to the University of Tennessee has been paid for completely by external funding of grants. And so the University of Tennessee and the state of Tennessee got completely our teaching, the thousands of students, completely for free. And I would claim that no athletics program can come close to doing anything like that. There are other faculty, though, that have done that. And so this is one of the benefits of active research programs. Now, of course, we did not build all this ourselves. There's lots of other people who've been very much involved in this. And these are some of the full-time staff from Nimbus, as well as from the Institute for Environmental Modeling, who really enabled us to get to the point of being successful as we have been in applying quantitative methods to many, many areas of biology. I could tell stories about each one of them. There's at least two in the room, and I will not mention them. I mean, I could tell stories, but you can ask me stories later. Okay. And so, it really, that's a bit of reminiscence about what has allowed us to be successful. Now I want to go on to the topic of this talk. And I want to emphasize a couple of items in the title. First of all, what does rational basis mean here? It means that there is a formal way of looking at the science that was underlying these connections between climate and the plans, how it impacts the future, and that there's a way to use scientific methodology and quantitative methods and using our best knowledge of, in this case, human behavior, and pulling it together so that there's a really rational basis for saying what will happen in the future. And then the hope part of this is that there's been, of course, as you know, a tremendous amount of concern about what the future holds in terms of climate issues. And in fact, this came out just a week and a half ago in the New York Times. It's called OK Doomer. Now, you may have heard OK Boomer, in which they're talking about people like my age and on. And it's kind of a critique, okay? In this case, it's a critique of people who are basically doomsayers, saying that there's nothing really that you can do. And this is a whole article, and one of the featured people in this article is Elena Wood. And Elena got her degree here at UTK in sustainability in 2017, and I know that she was in this room and did work at the Baker Center while she was here on campus. She was also heavily involved in recycling issues. This is an example of someone, she's a TikTok influencer. I'm not. It's impressive to me, okay? And so there is obviously a pushback towards this basically doom and gloom attitude. And the question is there a rational basis? Is there a way to say that science, yes, it's not as bad potentially as some of the sort of public perception is? So how do you go about dealing with these connections between social science and physical science in this case? Well, this is a picture from a call for proposals from the National Science Foundation from now almost 20 years ago from coupled natural systems. And it illustrates the point that there are connections between the sort of natural system, in this case that would be biological as well as physical system, and the human system. And the argument for this call for proposals was that this should be a way to connect the two, to bring them together, and that there'd be feedbacks back and forth between them. Now, this is challenging. It's why the National Science Foundation funded it. And it's challenging because there's several problems. First of all, there's kind of a mismatch of scales between the scales of the physical systems and the scales of the human system, both time and spatially. And frankly, the main conceptual tools that we have for dealing with biological and natural systems are pretty good. I mean, we know a fair amount about how physical systems work. We don't have quite as much concordance about the conceptual way to deal with human systems. There's lots of differences of that. And the rules for coupling these are not well known. So a group of us who are also involved in this other research have a paper coming out in Ecology and Society on that. I'm not going to say anything about this particular project. If you'd like to ask, we can have a conversation about it. But it does essentially analyze what is successful in building the kinds of coupled system models that allow you to link human and natural systems. And I will point to the group of people involved in the projects that I am going to talk about today as an example of success in carrying out this coupling between human systems and natural systems. So this is a group funded initially by NIMS, the institute here, and a joint collaboration with a sister synthesis center called SYSYNC, the Socio-Environmental Synthesis Center at University of Maryland. And I will just point out that this group of people includes economists, psychologists, demographers, of course modelers, people like me, climate scientists, physical scientists, and biologists. And that led to a follow-up kind of a group that focused a bit more on policy and economic issues that was also funded out of SYSYNC. And again, these are the people that are involved in the research that I'm going to sort of talk with you about today. Okay? So one measure of success of these things, of course, is whether you actually successfully publish the research. And so one of our first papers came out in Nature Climate Change now over 2 years ago, and another one was published in Climatic Change. And just last month, we had the most recent paper in Nature. Okay? So, and I'm going to talk a little bit about those papers, but my objective is to do this in a kind of a broad way to some extent. And I have to put up a picture like this just to reinforce the fact that indeed the physical models for climate do indicate that we are in a situation in which there will be significant increases in temperature. In this case, this is a projection till the end of this century, and it's a comparison to the average temperature. In this case, it was 1960 to 1990. And so where it's red, which is basically everywhere, there's a significant expectation that there will be increases in mean global temperature, or mean localized temperature in this case, localized, over the next 80 years or so. So that's the concern. So as an overview of this talk, I'm going to do a really quick summary of climate models. I'll say something about models for human behavior, and a particular one that we applied called the theory of planned behavior. Then I'll go on and talk about how we linked a human risk perception model to climate models and say something about what that means about projections for greenhouse gas emissions. And then I'll go on and talk about a the more recent modeling approach in which we looked at the formation of climate policy and how that arises from sort of fundamental social, political, and technical processes along the way. Our objective here is really to consider how human risk perception and behaviors arising from this might impact and interact with climate change. When we started working on this, now, oh gosh, almost 9 years ago, the question was, is there really any way that human responses to systems can ameliorate what has come to be concordance in the physical models? The physical models done by very different groups, and if you went back 30 years and you looked at what their projections were, there were very different ones. Those models have become very, very much concordant about this, the fact that we're in a very, very warming world, okay? Even though they're different models done by different groups with somewhat different emphases. So the question that we asked, and we did not, we didn't go into this with the knowledge as to what would come out, whether the potential feedbacks from human systems are really sufficient to have some significant impact on global climate, okay? And it's not clear. And so are there circumstances in which risk perception particularly would perhaps change people's attitudes sufficiently to measurably impact future climate? So I want to say something about climate models real quick. There's a bunch of different kinds. Right? The ones that you probably see most are the very, very complicated three-dimensional general circulation models, which are very well sort of categorized in terms of the physical components of the system. They have many layers that go up above the Earth. They include oceans. They're extremely well characterized. There's been enormous amounts of money spent on developing them. And they've had tremendous benefit because as that has happened, our capability to do weather prediction has also gone up. So when I was a kid, you would laugh at what the weather forecasters would say on television, okay? Because, you might as well flip a coin. That is no longer true, okay? And it's no longer true because the quality of these physical models is much more. And I just wanted to point out that there are a whole variety of other models that are used for these climate changes. But one of the challenges is that these models do not take into account at all the feedbacks from human social systems. They basically simply assume some trajectory of what humans are going to do, and they fix that, and that's it. Those are called representative carbon pathways or representative emissions pathways. That's the way that they work. They take a scenario, they assume that's it, and they plug it into the model, and then they see what that implies from the physics about what temperature is going to be. There are a set of what are called integrated assessment models, I'll show you a picture in a second, that do take into account various human activities, agricultural production, demography, movement, energy use, and something about their feedbacks on greenhouse gas emissions. But they also basically use some fixed scenario for human activity. So this is an image of one from MIT, which one of our collaborators, Adam Schlosser, is one of the developers of. And so there's lots of things going on in there. Okay, it is complicated. These integrated assessment models are not trivial, and we did use one of them in the first collection of papers I talked about. But there's really no feedback to human behavior in these things at all. Okay, so let's talk a little bit about how one goes about modeling human behavior. And there's a bunch of approaches, and I'm not going to try to summarize all of them. I do want to talk about a couple of them. So this is John von Neumann, one of the most brilliant mathematicians of the last century, and Oscar Morgenstern, an economist, and they wrote a classic book and developed a whole body of work on the theory of games, okay? And they applied it particularly to coalition formation and to economic behavior, groups of individuals, to humans. It's gone on, and the ideas have been taken and applied in loads of other contexts, including in evolutionary biology. And it's challenging to really apply this to something like climate change issues, but I do want to point out that it is there. So next person I'm going to mention is maybe somebody you wouldn't think of in this context. Isaac Asimov was a science fiction writer, but not just science fiction. He wrote, I got to remember, I think it's over 1,000 books in his lifetime. It was amazing what he did. An extremely bright fellow. I only met him once. It was one of the highlights of my younger days. He wrote a whole series of books. It's probably the most famous science fiction series. It's called the Foundation series, and that's my collection of some of them. And if you go to Apple TV, there's a brand new series that attempts to, attempts to mimic what's going on in these stories. If you want to talk about how I feel about that series, I'm happy to do it. But I did want to point out that in the first volume of this, okay, and the idea is that there was this Encyclopedia Galactica, and I'm going to read this quote here. It talks about the branch of mathematics called psychohistory, which Isaac Asimov made up, okay, which deals with the reactions of human conglomerates to fixed social and economic stimuli, and implicit is the assumption that the human conglomerate being dealt with is sufficiently large for valid statistical treatment. So this idea that Asimov has in this book is that you can analyze human behavior if you have a large enough collection of humans in order to sort of build what they call the laws, the theorems for how this works, this psychohistory works. And the hero of that was Harry Selden in these books. That's one sort of picture of what Harry Selden might have looked like. And he's a mathematician. Now, as a naive young, middle schooler, and I'm reading this book, a hero who's a mathematician. Wow, that's possible. Okay, so mathematicians are usually thought of as complete nerds. So I thought this is cool, and so I read this and took it to heart and became a mathematician. And as it turns out, later on, now 30 years ago, Don DeAngelis and I edited the first volume that took this kind of approach. It's now called agent-based modeling or individual-based modeling, in which you actually model a conglomerate of individuals based upon the rules for interactions between them. And it's applied now to many, many, many different situations, a whole field of agent-based modeling around. And so that's a direct outcome of Foundation to some extent. But that's one way of analyzing human behavior and its impacts. There's a whole journal, okay, called JAS. It's the Journal of Artificial Societies and Social Simulation. Many of the papers, not all, but many of them use this agent-based approach in there. And I do want to point out that there are other ways of sort of thinking about modeling human behavior. One of the best papers, Marta Schluter published this with a whole group of people in ecological economics. We call it the MoHub paper for basically modeling human behavior. Okay? And they go through the characterizations that one could do. And one of those characterizations, this is the theory of planned behavior, which was developed by Aichen, this is back over in the early 90s, and it comes out of psychology, and it's a way of considering the combination of ideas between attitudes, what are called perceived social norm, and perceived behavioral control, and I'll define those things, and how those interact to influence behavior. So the notion that Aichen had is that attitudes are people's positive or negative evaluation of behaviors. In terms of climate change, it would be towards policies that mitigate CO2 or greenhouse gas emission. And it's comprised of a couple of components. One being risk perception, how indeed individuals perceive the potential risk to themselves, their offspring, and future due to the adverse effects of climate, as well as perceived efficacy, which means it's the extent to which one believes that they can actually have a behavior that influences greenhouse gas emissions. And what is called perceived social norm is the fact that your perception of what other people are doing. So if I suddenly put on a mask, say, oh, everybody should put it, then the social norm in the room might have changed, okay? Might have, right? So it's a perception of how a behavior is performed and approved of by others in the group that interact. Perceived behavioral control is part of this. It refers to people's perception of how much control they have over whether or not they perform a behavior. Okay? Obviously, if you're in a totalitarian state, you have very little control as compared to a state in which you actually have more perceived control. Okay? And the sort of picture of this theory of planned behavior is that there's interactions between these. And this is basically the status of the theory in some sense. It's a kind of graphical kind of a theory. And what we wanted to do was to turn it into mathematics, to turn it into a way of thinking about how social systems and so on interact and how they change. And so what we did is, this is the Nature Climate Change paper. I'm going to go through this, but basically it's a cyclical kind of piece, and I'll go through each piece, but it is linked to one of these integrated assessment climate models. It's called C-ROADS, and the C-ROADS part of this is the climate piece, which we didn't develop. We're using that as it comes along. And so the pieces of this thing are, it has, first of all, the frequency of extreme events. Extreme events are things that may drive your perception of the world changing, and the usual things would be hurricanes, droughts, major fires, those sorts of things. There's the way that humans sense this, and then there's the way that you forget them, okay? And there's, of course, we have collaborators who are the psychologists who have pretty good ideas about these aspects of human sensing. And that leads to a way of keeping track, and so we have a pool here that keeps track of how many of these events are in memory, broadly speaking. And that leads to a perception of how risky it is in the future if nothing changes. And then there's a variety of functional forms that drive this that I won't worry about. And then this goes to the concept of efficacy and your perception of whether or not behavior really does affect greenhouse gas emissions. There's the attitudes, meaning how you interact with others and relative to the action of the behaviors you carry out. There's a perceived social norm, meaning your perception of what other people are doing, okay? And perceived behavioral control, again, whether or not you actually feel that you perceive you have any control over this. And there's the emissions behavior change. That means these all lead into changes to behavior that's up there on that side. And that leads into impacting greenhouse gas emissions, okay? Which then ties into a global climate model and then comes back to giving you an estimate of mean global temperature. This is a global model, right? It's not disaggregated spatially or anything like that. So it's not that complicated. Although, you know, it's got a kind of a handful of parameters that are changed. So here's the key assumptions in this. Key assumptions are that human behaviors feed back to climate through a modification in carbon emissions, okay? And so the only human feedbacks here, there's no economics in this one, okay? The feedbacks are just to carbon emission. The human behavioral responses arise from perceptions of risk associated with experiencing extreme events. And there's a statistical model we have underlying this based upon data about the number of extreme events and how those are characterized as a function of average global temperature. So we actually have data on that that we developed a model for. And then how the modifications to emissions due to these behavioral feedbacks are maintained in terms of a pool of cumulative changes of carbon emissions. And we make some assumption that there's some minimum level of carbon emissions globally that can't be changed, okay? We can modify that. So what are the kinds of results out of this? So there's a number of things going on in this graph. I'm going to talk you through it. First of all, the black line here that's sort of in between the red there, okay? That black line is a baseline. That is the baseline carbon emissions that is projected to occur without any major changes in greenhouse gas emissions or anything else. And so this is the time period here is from now up to 2100. And the degree centigrade on the vertical axis there is the comparison of change of mean global temperature in each one of these years to pre-industrial. That's one of the, there's a number of different comparison time periods. This one is pre-industrial, meaning 1850 to 1860 in that time period, estimates of that. So what the model does is it allows us to vary using what the social model components do and compare it to alternatives. So the lowest one here, and you note that they're all increasing, okay? Even if, so that lowest one there says that there's no additional emissions at all, okay, beyond what we have right now. Even if there's no additional emissions, this model, based upon the carbon part of it, says that we're still going to have increases in temperature significantly. We're right now somewhere around 1.4 degrees Celsius above the pre-industrial, and it's going to increase, okay? Based upon the carbon model here. And the question is, how does that compare to the baseline, which is in black, which is essentially the business as usual? We're continuing to basically have carbon releases at the same rate that we are now, and that it's climbing as a rate as it has been over the last 10 to 20 years or so. Note that if you just increase or decrease carbon emissions by 5%, that's the little B and C, it does basically nothing to change the sort of future trajectories of temperature. What our model, though, does is it ranges, what this social model does is that it ranges from this green line here to that upper green line. The upper one says that when you account for behavior, things can get worse. Okay? In other words, we did not construct this model in a way that it was always going to reduce carbon emissions. Otherwise, it wouldn't be appropriate if we did that. So that upper green line is the case in which everybody says, the hell with it. I'm buying an SUV. I don't care. And, oh, sorry. There's good SUVs now. Wow, good. There's better SUVs now. Okay, so at any rate, it's possible in this to get really worse, but it's also possible to get really much better. That's this lower green line there. In other words, there is some rational basis using this kind of model to say that climate change will not be quite as bad as it will be under the baseline scenario. And I just put this up because this is just to talk about an approach. It's called a regression tree approach, in which there's about 5 or 6 parameters in this that we don't have good handles on. So you run lots of simulations, and then you see how the combinations of those parameters affect on the lower axis here how much the global temperature is at 2100, mean global temperature. And you can see there's quite a range. It's about almost 2 degrees. And so there are social interaction scenarios in which this really does impact it. So some conclusions from this. Integrated human behavioral and climate model results indicate that you can have global temperature changes ranging from 3.4 to 6.2 by 2100 compared to the sort of baseline of 4.9. So there is the potential, due to the feedbacks, to lead to much lower carbon emissions and lower global temperature, also higher ones, okay? The cumulative infrastructure change is what significantly happens when you lower it. It means that just turning off lights is not sufficient, okay? It means that one does need to have cumulative change that builds the infrastructure, in this case, electric cars. I mean, that's one example of that. That leads to this, that it's not going to work just by lowering the amount of mileage that people drive, okay? That the magnitude of the behavioral uncertainty in this kind of a model was similar to the magnitude of the uncertainty in the physical models. What this says is that the accounting for human behavior in these models leads to as much uncertainty, not really much more, than the physical model uncertainty. And we spend an awful lot of time thinking about the physical models, and it says that we should probably be investing a lot more time thinking about the behavioral things which are challenging, but they're not nearly as invested in. And there are a set of social components that we can identify which have the largest influence, particularly perceived social norms. And the attribution of extreme events to climate change and infrastructure is what really matters. So we have this field of what's called attribution science now, in which you can actually come up with a formal statistical and physical modeling approach which says this particular set of climate events would likely not have happened, and assign a probability to it if climate change had not been going on. Okay, so that's called attribution science. And if someone's interested, we can talk about suggestions of how we foster this. If we have time to do that. I'm going to move on though quickly to this most recent paper. One of the things that I feel most strongly about with regard to modeling is that multiple models are good. That if you have an underlying problem and you approach it from two different approaches and you come up with similar results, that provides further evidence that indeed things are going on. So what we did is we took a very different approach. It's not the theory of planned behavior at all, but what we wanted to do was to incorporate economics and model the formation of climate policy, which was not in the previous version of the model at all, as the outcome of basically more fundamental processes of social and political things. And then we basically systematically explore the space of model dynamics, and we constrain a set of model parameters and run the model forward to generate what we call storylines, basically, of emissions. And so this is a backwards approach from what the standard approach is. Standard approach is you have a representative pathway, you assume emissions do this. We're doing the reverse. We're saying, in this model, what are the stories that emerge? And we characterize the kinds of future trajectories of human behavior that would drive climate emissions. And this uses a system dynamics modeling approach. Now, this is a kind of caricature of the model, but I put this up to indicate that it is not that complicated. There's lots of things going on in this, but the number of sort of components to it are pretty small. There's a climate piece, of course. There is perception and cognition. There's opinions. They're like the attitudes that we had before, and they're driven by policies and whether or not those policies are adopted or not. And there's emissions, and those policies are driven in part by economics in this. And because I'm not supposed to go on too much longer, I'm going to go through this fairly quickly. Otherwise, I don't know whether Charles is going to come up and pull me off stage or not. But these are the components in this approach, and I'm just going to indicate some of them and not put down any mathematics or anything like that. So, for example, here's the opinion piece. And so in the opinion piece, we disaggregate the world into opinion groups which are either support, neutral, or oppose changes in behavior that lead to greenhouse gas mitigation. So it's a typical breakdown. Just if you've ever done epidemic modeling or anything like that, you have susceptible, infected, and removed. Well, these are political sort of opinion groups, okay? And then the size of the groups evolve based on the interactions with all the other components and a social network that may be different from the population depending upon what's called the homophilia. That's the tendency to preferentially associate with people like you, okay, which is a common idea, of course. And then there's a whole set of component feedbacks between the components, the major ones that affect the opinion piece. And then there's an adoption piece to this, in which individual decision to adopt a single pro-climate behavior changes. There's a form that's called logistic form that we utilize for that. And it can be affected by opinion on climate policy. So different opinion groups impact this adoption feedback. And the social norm depends on the social network piece. So that's another piece. And there's also another component to this, which is policy, and this has to do with changes in the carbon price. So we basically think of the stock variable that represents this policy component as a carbon price. Okay, and so again, this ties in a bit to the economics of it. One of the other aspects of this model that's different is that it really does have components that operate on quite different scales. The cognition piece operates at the individual scale. The social scale is behavioral change and public opinion, and it goes up to global scale where it's climate and emissions. So there really are some differences here, and it's not disaggregated globally in any sense, but it should. But our objective here was to sort of point out that there are these connections, okay, that operate at different scales. So what do we do with this? So we project climate futures. We run the model. There's a whole set of calibration of this model to actual data, which I'm not going to talk about. So you calibrate it first to a couple of different opinion and policy data sets, and run a bunch of simulations. They're called Monte Carlo samples, in which you randomly choose a whole bunch of different parameters there's about 25 different parameters in this, randomly choose them, and you sample a whole bunch of them. And unlike the previous case, in which we had a handful of parameters, here you got about 25. You can't really do a regression tree kind of approach that characterizes it. What we do instead is what's called a clustering approach. This is straight out of now machine learning things, in which you could actually look at these 100,000 or so Monte Carlo runs and see whether or not there are actually distinct clusters of them with similar characteristics in some sense, and whether those groups that are of similar characteristics arrive, or whether you just have a bloody continuum where everything is, mishmashed together. We didn't know, by the way. Okay, and there is a Shiny app. It's freely available. You can go in and you can change these parameters and make your runs and see how that affects opinions. What fraction of people are in different opinion groups. The results here, and I'll just talk about the right-hand slide here. So this is from running the 100,000 or so runs, doing the clustering, and the clustering leads to quite distinct groups. In other words, there's not really a continuum across this 25-dimensional space of parameters at all. And we characterize this as what could be called a modal path, an aggressive action path, a technical challenge path, a delayed recognition path, meaning, oh, yeah, we realize there's something wrong, but we're not doing with it right yet. And little and late, that means we're not going to do very much, and we're doing it too late, okay? And that's the upper one there, okay? So in that case, emissions go on. We did not know that indeed we would be able to characterize future trajectories in this sort of relatively small number of characterizations of sort of groups of behavior. Okay. So the results from this is in the recent Nature paper, is that first of all, climate policy and emissions can be analyzed as arising from these interactions between these fundamental ideas of policy, political and technical processes, and there's strong evidence that there really are distinct clusters of future trajectory behaviors. Okay? That it's not everything that can happen. Okay? That there really are feedbacks between the multiple scales that require representation at the individual social, national, and global processes. And those feedbacks really do lead to very significant changes in projected trajectories. And I didn't talk about it, but the model does have tipping points. In other words, the mathematicians will call them bifurcations, in which basically there is a sudden change in behavior with a small change in a parameter. Okay? And that can arise in this model. There's lots of nonlinearities. There's lots of feedbacks in this. Okay? We weren't, again, sure that was going to happen. And that we can basically build storylines of future climates that we observe as these clusters of model responses, and we can really view them as representative emissions pathways, but due to behavior. They're not forced on the system exogenously. They're coming endogenously from the model itself. Okay? And in terms of global temperature conclusions, there's a variety of parameter uncertainties here, but none of the sort of policies and clusters of emissions really identified what would be called a pure business as usual scenario. That they all actually had reductions in projected mean temperature. Even the highest emission cluster produces a warming that's lower than the sort of standard representative carbon pathway that I pointed out there of 3.9 degrees Celsius. And the vast majority of the runs here produce warming of more than half a degree lower than what would be expected under the business as usual case. And the identified emissions trajectories, even the aggressive active scenarios, really don't meet the hopeful 1.5 degrees Celsius increase. But a significant fraction actually do, that's like 28% of the runs, actually do hit that a 2% target above the 1880 or so runs. So, I mean, basically this provides further evidence. It's a completely different model. It does provide further evidence that there's some hope. Now, what do we do next? Well, in our paper, it came out in Climatic Change, we argued that we're dealing with one set of behavioral theories. There's a need really to build a whole collection of these behavioral models, link them to different climate models, and to focus a bit on the social components of this, which has not been really focused on at all, and to build what we would call a social sciences model intercomparison project. There's a standard set of intercomparison projects for the physical models, and it's not there for the social piece. Okay? So in sum, there is some rational basis for hope, okay? Because both these models, done somewhat independently with different structure, lead to results that indicate that there can be futures with significantly lower mean global temperature than the standard sort of business as usual expectations. Okay, and the next steps will require us to not fear this linkage of social dynamics and to work to overcome the barriers of incorporating human behavior into climate models. So I hope that this leads you to some better perception that there is some hope and that it's not just the doomer mentality, that there is some basis for a scientific rational basis for hope in this case, and that individual behaviors do matter, okay? There are certain things we have not included in our models. We don't have celebrity factor in there, for example, okay? But we know how to do that, and we're still working on this. This is a group of projects that are still going on. And I'm out of time. I'm probably over time, but Charles said, you can keep going. In that case, I do want to say one thing. You may have heard that there is a bill that I don't know if the governor has signed yet in Tennessee about a civics institute, American Civics Institute. There's been a good deal of controversy about that. The argument is that that's going to be located here in the Baker Center, and it is an opportunity for the Baker Center to contribute to perhaps understanding the discord that is ongoing across our society. And I would argue, based upon the kinds of things that we've done, that this is a perfect opportunity for the Baker Center to think about the field of the mathematics of civil discord. Civil discussions, I'll call it that, discourse. So the mathematics of civil discourse would apply what we know about social processes, and Sergei Gavrilets is in the room, and it directs a whole institute on the dynamics of social systems, and there are other people on campus too. And this provides a wonderful opportunity for the Baker Center to carry out this new field of thinking about how we can more rationally have discussions with each other about controversial topics using mathematics. And not only is it an interesting potential new field that this place could become a world leading center at, But whenever you say the mathematics of something, it means the politicians don't pay attention. So thank you very much for being here. I really appreciate it, and it's been wonderful being here on the faculty, and I've just had a great time, and will continue to. I will be emeritus, so thank you.
So Lou, thanks for the kind words about the center. It's almost like you were listening to a meeting I was in yesterday where I was saying the same thing. Also saying that we won't put mathematics in the title anywhere because that would be a bad idea for getting any sort of buy-in. So it is almost like you bugged the room. So we've got lots of questions here online coming in from all the people that are watching online. And we have room here in the auditorium for questions for Dr. Gross. Step right up to the mic and we can do those. I wanted to start, though. I'm going to step in front of Paul. I wanted to start, though, by pointing out that the number one question that we get in this forum when we talk about climate change is, and it's here, there's 2 or 3 of them in here. There's a whole group of questions in here that are about this. What can I do on a day-to-day basis to help combat climate change? And everybody gives a different answer when they're in here. I mean, we get one of these questions every year, and everybody gives a different answer about, you can do something, turn your lights off, or turn your thermostats down, or go buy an electric car, or no, you can't really do anything. This is a collective action problem. Just bury your head in your pillow and cry and wait for the politicians to do something, right? But you clearly have a model here that lets us tease out the degree to which we are in that spectrum between throw up your hands and do nothing and wait on the politicians, or actually sit down and do something. So I just wanted to point out that this is a question that comes up a lot. People are wanting to hear this. So even if you don't do a lot of modeling yourself, fundamentally, everybody who hears about climate change wants to know, where are we on that spectrum? So
it is a great question, and I will give a couple of responses. So one is that I do encourage you, if you've not heard of this OK Doomer stuff, to actually go. This is a group of young people. It's not just Elena Wood. There's a whole group of young people who do make this argument that individual action can lead to collective behavior that does have impact. And our models are consistent with that, okay? But our models also indicate that the type of action that does happen does matter. That cumulative impacts really do matter. And that does mean moving towards not just reducing the number of miles that you drive and so on, but it really does mean infrastructural changes. Okay? And that they, in terms of the model results in that first collection of models, that they have big impact. The other, and of course, there are lots of suggestions on various websites about how to do this. The other aspect of this is the social system aspect of this, that until there is a strong political will to make a change, that may not happen. Sometimes that political will arises due to economics that was not really perceived as leading to that. So I would say that if you thought back 10 years ago, do you think that you would see that right now the number of electric vehicles being purchased is much, much higher than probably most of us thought was feasible? How did that happen? And studying how that happens leads to a way of understanding what is potential in terms of change. And of course, the subsidies that were passed did have an impact on that. But how much of it was subsidies? How much of it was driven by individual concern for, I want to buy an electric vehicle? I don't think we actually have the answer to that yet. Okay, there are a whole host of some of my colleagues who are psychologists actually looking at those kinds of results. I will mention one other thing too, and that is that one of our suggestions has been that to change public attitudes, you have to think about who broadly the public respects and might modify their thinking because of something that is stated. And this is a U.S. perspective, by the way. The U.S. is not the whole world, okay? And that there are really different social groupings with very different, and we'd like to do some disaggregated modeling. But in the U.S. perspective, the general populace, I go out and walk around East Tennessee and talk to people, I'm a egghead, okay? And I'm here on the faculty. I've been here my whole career, you know. I'm not that respected. Well, I mean, I might be respected in certain communities. Maybe the dance community wouldn't respect me, but not because of this. So who do people respect? Well, you may remember I mentioned the fact that our big climate models have now enhanced our capability to predict weather. When you ask people who is the sort of scientifically trained person that they most respect, it's the meteorologist on your local TV station, okay? And so we stated in this that, oh, well, maybe if we can somehow encourage meteorologists to point out that, oh, this set of fires that we have been having is really due to climate change. And just saying that could enhance the likelihood that attitudes change. Well, it turns out we're not the only people that had that idea. There's a whole group called Climate Action. And Climate Action has taken on the goal of providing detailed scientific evidence for local weather station, weather reporters, local meteorologists, that they can use locally and be able to attribute what's going on to what's going on. I was interviewed by Ben Cathy, who's at WVLT, on some of this stuff when the Nature paper came out, and he said, "Oh yeah, I use that." Okay, and so what they've done is figured out a way to encourage those who are influencers in a different way from the TikTok influencers to actually lead to sort of attitudinal change. Okay, so that's a long-winded answer to that question, but I hope it was somewhat enlightening to the people listening. Okay. Oh no.
So thinking about the clustering method in the second analysis. So I can imagine that approach, you have to look at base expectations. I would expect you'll get back aggregates of parameters that kind of move together, like we would have gotten from a simpler model with non-dimensionalization. You'll get some
whoops, it's not on.
So back up. So on the clustering analysis in the second paper, I'm thinking about what you might get back, Lou. I can see that you could get, and I would expect to get, sort of aggregates of parameters that act in sync with one another. Mm-hmm. But you have the potential in that method to get something quite different that other approaches wouldn't have given. Do you ever see scenarios coming together in a cluster that are actually really different in what they're describing about society?
Yeah, so that's a very good question. And we have a whole table in this paper of the key sort of parameters in each one of those broad sets of clusters which are driving the cluster. And by the way, we were not sure that, I get your intuition that there might be a small number of parameters that drive a whole set of future trajectories, but it wasn't clear to us that would necessarily arise. It's a fairly complicated set of feedbacks in here, okay? But it did characterize that way, and it provides some guidance to us in terms of then looking at these are the key components and digging into them. And we didn't do very much of that in this paper yet. But these are the key components that are driving this cluster. And then you can look into the details of those and how they interact in the model, and perhaps, well, I would say target research surveys on those particular items. That's one of the goals of doing that.
How did you include technology in this model?
Oh, yeah. So, it's represented in this.
So the question was, how did he include technology in the model? Just repeat it so everybody online can hear.
Yeah. So it has to do with the climate the carbon and the economic pieces of this in terms of policy affecting the carbon subsidy piece. It's not really tech. I mean, we don't have nuclear plants. I mean, we just have, it's a very broad model in that sense, okay?
Try different scenarios for that?
Oh, there's parameters that guide, yeah. Again, there's like 25 parameters. I think I showed that image of the Shiny app that allows you to go in and change these, and some of them were specifically on that carbon price piece of it that is driven by technology.
So Lou, I've got a bunch of questions online that I will generally group them into a category called policy pendulum swings. Okay, so there's lots of questions about what does a presidential term do to our moves? And so one thing this makes me think of is you talked about how there were tipping points in your models.
Thanks a lot, everybody, those that have to leave, yeah.
You talked about how there were tipping points, behavioral tipping points in your model. Did you also find evidence of cyclical behavior anywhere, where you might think of this as moving back and forth between a pro-climate administration versus a not so pro-climate administration?
Yeah, so that what we would call non-autonomous behavior, okay, is not built into the model because there's no underlying politics associated with regime change or anything like that in terms of the political situation. So I can't say there's none, but I don't recall anything about cyclical phenomena occurring in this. Of course, it's certainly possible that it could arise. I'm just not seeing it. And so much of this is the driver, okay, and the drivers are the perception of additional risk associated with enhanced global temperatures that drive this. And those feedbacks are really what's critical to leading to the sort of hopeful attitude that things are going to not be quite as bad as they could be. Okay.
Hi, Lou.
Hi.
So Paul asked a math question, and I would like to ask a stats question. So looks like from the regression tree, PSN, the perceived social norm, was probably the most important.
Yep.
Because it was the first split, right?
Yep, that was the first split. Yep.
So that's super interesting to me, and sounds like your idea of having TikTok influencers would help in that for sure, because it's the most important factor.
Yeah.
I wonder, like with increasing divisiveness, how do you think that particular variable might actually affect? Because right now you're looking at perceived social norms as like a single parameter.
In that model, it was.
Yeah.
Okay.
But with divisiveness, how would that like pull apart that variable into like perhaps two different variables where increasing divisiveness might cause like one group of people to be like, so the distribution of the social norms might change, and how might that affect?
So this deals, okay, of course, with, and so the first model, which you talked about with regard to the regression tree, basically was really simple with regard to the perceived social norm, okay? It was a parameter that we mucked with in there, and it was a parameter split. The second model does not do that, okay? It really does have different opinion groups, and how much those opinion groups interact with each other versus with each other, that's another parameter in there, and that does affect whether or not you really do get sort of separation or not in that second model, okay? So we have tried to incorporate that, and this is why the second model is really different from that first one. And by the way, there's another whole set of them we're working on too. Not ready for prime time yet.
So the mean perceived social norm, so in the second study, the mean perceived social norm was the same, but with divisiveness, with the amount of crosstalk in the different groups, like with reduction in that crosstalk, will that increase the amount of emissions?
Okay, so the question is the following. This is in the second paper, and not where there's a disaggregated set of opinion groups. So there's a disaggregated set of opinion groups, and therefore different social norms because they're interacting potentially with different ones. And if they're really completely separate, okay, I mean, if they were really completely separate, all right, then you wouldn't expect much of any change in those opinion groups over time unless there's something else driving them, like economics, okay, which could, in that model, do that. But if indeed they're interacting, I mean, this is the homophily piece of it, how much interaction there is between them, then that does lead to a more of a higher rate of reduction of greenhouse gas emissions. Oh, we have a question here. Do you want to use the microphone?
Thank you. In your quantitative descriptions of the results of these assessments, it seemed like for climate change, there was an increase in the climate temperature in spite of everything else that you've taken account of in the model.
Yep.
Do you have any clue as to what's causing that?
Oh, yeah, sure. So that comes out of straight, that's a good question. So the challenge is that the world that we live in, okay, has a trajectory that even if we completely stop greenhouse gas emissions, that trajectory is continuing for quite a long time. And that you saw that in even what was called the 0 gigaton release one. And that's pure physics. Okay, there's nothing in that has to do with human behavior at all. It is the physical models. And they all pretty much consistently agree now on that. They didn't always initially, but there is this, it would be typically called a time lag and response of the Earth system because of the buildup of greenhouse gas. So right now, the atmospheric greenhouse gas concentration is, let's see, it's like 410, 420 parts. It depends where you are and what. And when I was a kid, it was 325. Okay? So even if you stop greenhouse gas emissions completely, that's going to continue to go up for some time period until it slowly, and we can't stop. I mean, obviously, we can't feasibly do it. But it's a great question. And the detailed physics of it, that's actually beyond me, okay, in the sense of I'm not a global climate modeler, but we could probably sit down and look at some of those papers and see what's really going on.
But it seems like it might be possible to include that in your calculations as well then.
It's already in there in the sense that these are relying, so the behavioral models are linked to the physical models, and those physical models already have that component built in. That's a good question. That, they're already in there because they're in the physical model pieces. Okay.
Another question: can you describe the tools that you use to do all this work?
That's a great question, boy. So this ties in to that other paper that I mentioned. What we did is we looked at the people who were funded by the National Science Foundation to account for these linkages back and forth between human systems and natural systems. They were funded to do that. And the question was, how successful were they at doing this? So we did this by, there were, I can't remember how many, there's something like 300 or 400 funded projects. We didn't look at all 300 or 400. We pulled a sample of those and pulled a sample of the papers that they published, and then had people do what's called coding. This is not mathematical. It's not program coding. It's looking at them and deciding, does this include a linkage from here to here? Does it include a linkage back? And doing that sort of in a sort of standardized way. And then you have checking, cross-referencing, checking between individuals. And it turns out that very few of those funded projects actually had links back in both directions. Many of them had linkages one way, but not back. It turns out that it's really hard to do that. And what were the success routes? In other words, what were the tools that people used to lead to successful real feedbacks in both directions? And frankly, it was people who were really interdisciplinary, who really did have their feet in the economics camp and in the modeling camp and in the climate camp. In other words, having people involved who were really interdisciplinary, and we're not just sitting down at a table and you have a psychologist trying to talk to a modeler, trying to talk to a climate scientist, that having somebody that can talk and foster the language of communication across them was a key tool. And we didn't know that this was going to happen, by the way, at all. I mean, we also had no idea how many of these papers actually did have these cross-linkages, and it turns out relatively few of them did. It actually is one reason why the National Science Foundation has changed that program, okay? Because they also saw that it wasn't doing exactly what they wanted. Now that's about the people tool. I'm calling the people tools part of this. What works in successful interdisciplinary collaboration? And there's a whole field called the science of team science that deals with trying to understand what leads to success in collaboration. And it's really important in a world in which we have teams of people doing things together all the time. But that's not about the technical tools. The technical tools are the coding tools and the computational tools, and that's another whole bailiwick, which we could talk about if you want to. But you want that? Okay. So this field, sure. So first of all, what is modeling? Modeling is the use of mathematical underlying concepts to develop ways to think about complex systems, to think about how systems interact. And the fields of mathematics build upon calculus there, the old calculus and what is called differential equations. It's generally called dynamical systems. And what they do is that they allow you to consider how different components, different variables, so think of policy, opinion, cognition, and so on, how they interact and how they drive each other in this system. And so there's a set of equations that allows you to do that. Then there's the data piece. How do you actually compare the kinds of results that you have to the limited data? And we used a couple of different data sets associated with Sweden and a couple of other countries. And that's a general field of what would be called data science in general, okay? So data science is a use of quantitative methods to take data and to analyze the results and to also use them to parameterize models, to tell you what's an appropriate form or function to use. And so that's the sort of data science piece, and statistics is often considered part of data science, although some of my colleagues here in business analytics and statistics might argue with that, but I'll let them make that argument. And then there's the computing pieces of this, okay? In other words, how do you implement all this stuff on a computer? And so, for example, in that last set of code, we used R, which is a language that allows you to actually write out, it's a computer language code. In the first set of papers, though, we didn't use that. We used what's called a system dynamics framework. And this is a set of software that allows you to do graphical modeling and automatically do the sort of connections between them in a differential equations framework, although it's in discrete time. Sorry, that was a long-winded answer.
And one final question. Are people or are you working on applying this methodology to something other than climate change?
Yes, so we were just requested. So we sent in a little request, and Charles is involved in this, to the National Science Foundation, who put out a call for using basically linkages of human behavior to infectious disease modeling. Now, there is a long history of that. In fact, at the Institute I directed, one of our earliest projects was coming up with ways to link human behavior to infectious disease modeling. And the National Science Foundation has put out a call to do more of that, and actually some of us are writing, hopefully, a proposal very soon to respond to that, because it's due in a month. So yes, so in this case, it's not applied to climate stuff, but it's a similar set of ideas about human behavior and how to link them to, in this case, infectious disease. Different time scales, different. Thanks a lot for those questions. I appreciate it.
Well, I know Lou could go on all day if we let him.
Oh, yeah.
Lou, thank you for doing this. This is really nice. The campus is not going to be the same without you.
Oh.
I know that when I came here in 2013, one of the things that I got excited about was coming to work with folks at Nimbus. And when I interviewed here, you were giving a talk in Nimbus. Econ took me over there and let me sit through your seminar. And I remember from that point on, I was like, yeah, I want to come to UT. So Nimbus has been a big deal at UT for a while, and it's not going to be the same to have you gone. But with that, before we get all weepy here, join me in thanking Lou Gross one more time. Thank you.
My pleasure. Thanks a lot. All right. Thanks a lot for